Okay, so this is the second module on model building in the GLM. So if you recall, we've been talking about a standard GLM model which can be written as y equal to x beta plus epsilon, where epsilon is normally distributed with mean 0 and variance-covariance matrix V. Now, we discussed how the quality of the GLM, how well it would fit the data, depends on our choice of both the design matrix X and the variance-covariance matrix V. So last time we started talking about different ways, different components that we could include in our design matrix in order to ensure that we got a good model. So we talked a little bit about temporal basis sets and things like that. Today we're going to talk about nuisance covariance that should be included in the model. So often model factors that are associated with known sources of variability but are not related to the experimental hypothesis per se need to also be included in the GLM. An example of such possible nuisance regressors include the signal drift that we see when we put a person in the scanner, physiological artifacts such as respiration or heart rate, and also head motion. For those 6 regressors comprising of the 3 translations and 3 rotations are often put into the GLM as well. And sometimes transformation of these 6 regressors are also included. For example, the first difference or the squared or the square of the first difference. So oftentimes people can put up to 24 different motion regressors into the model. So as you'll recall when we were talking about the bolt signal, the slow changes in voxel intensity over time, which corresponds to low frequency noise, is always present in the fMRI signal. We call this drift. And so below here we see an example of a drifting signal. And scanner instabilities and not motion or physiological noise is thought to be the main cause of drift, as drift has been seen in dead bodies and in phantoms. Now, it's important for us to include drift parameters in our GLM model, and the way we can do this is, for example, we can model the drift using a series of splines or polynomial bases or discrete cosine bases. Here's an example of a model with drift. So if you look at the design matrix, the first column corresponds to the task, which is kind of an on-off block paradigm involved with the HRF. Then we have a baseline in the second column, and then after that we have a series of discrete cosine basis sets that model the drift. In total we have 9 different cosine basis sets here, and they're able to pick up very wide variety of different possible drift shapes. Okay, here's an example of the design matrix with drift fit to some simulated data. So the simulated data can be seen in blue in this figure to the right. And basically, let's look at 3 different possible models. One that incorporates just the task and the baseline, one that incorporates just the drift, and one that incorporates both. So if we look at the one that just incorporates the task, we get the red curve here. If we look at the one that just incorporates the drift, we get this black curve here. And if we look at the combination, we get this green curve here. And as you see, the green curve fits the data very well, while both the black and the red curve are missing central ingredients. Physiological noise such as respiration and heartbeat give rise to high frequency noise. It can potentially be modeled, especially if you kind of have machinery hooked up to measure your heart rate and respiration while you're collecting the scans. However, if you don't have that, often the TR of the experiments, the time resolution, is too low in order to appropriately model respiration and heart rate, and there'll be problems with aliasing. So in order to properly model heart rate and respiration, the sampling rate must be at least twice as big as the frequency of the curve you seek to model, according to something called the Nyquist criteria. And because your heart beats maybe once a second, we would have to sample every half second in order to recoup that signal. However, when our TR is 2 seconds, we're not going to be able to capture that signal. And so often this type of noise is difficult to remove and is often left in the data and thus give rise to temporal autocorrelations. And we'll talk about next module how to model that. Of course, as we talked about in the pre-processing modules, subject motion during the experiment can give rise to serious problems. And so typically motion correction is performed in the pre-processing stages of the analysis. However, spin history artifacts may remain that cannot be removed, and the spin history artifacts are caused by through-plane motion. So often people incorporate head motion parameters into their GLM, and it's found to give much better results. Here are the head motion parameters estimated from an experiment. So we have 6 different parameters, translations in the x-y directions and rotations in around 3 axes. These are often called pitch, roll, and yaw. Here's an example of some real data where we fit 2 models, one incorporating the motion parameters and one not. And as you can see in the uncorrected, the ones that didn't incorporate the motion parameters, we get a lot of noise all over the brain. However, when we correct for that and basically control for the motion, we get more regional activation. Okay, so that's the end of this module. It's the second of 2 modules on designing the design matrix, so to speak, in a GLM analysis. In the next module, we'll talk about how to design the variance-covariance matrix in the appropriate manner. Okay, I'll see you then. Bye.